Hey everyone, and welcome to This Explainer. Today, we're diving into one of the absolute most explosive, fascinating concepts in frontier AI, recursive self-improvement, or RSI. I mean, the basic idea sounds like straight-up science fiction, right? What actually happens when an AI can write its own code, generate its own data, diagnose its own weaknesses, and then turn around and train its own successor? Well, we're going to break down this incredibly complex topic. And as you'll see, we're going to uncover why this whole thing is about so much more than just making our models bigger.
So let's just get right to it and shatter a pretty big myth to anchor our whole discussion. Recursive self-improvement is not just a capability problem. As we scale these systems up, the central bottleneck completely shifts. It literally becomes a control, a verification, and a drift problem.
Which brings us to the million-dollar question, right? If AI can teach itself, what keeps the teaching process true? We spend so much of our time talking about the hype of capability scaling, but we kind of tend to ignore the hidden dangers of a self-teaching system. I mean, once an AI is creating its own tasks, designing its own tests, and updating its own behavior, how do we actually know it's getting better, rather than just figuring out how to trick itself?
Okay, here's our roadmap for today. We're going to hit 1. The recursive control problem. 2. The energetic paradigm. 3. Solving recursive drift. 4. Scientific taste and discovery. 5. Governing agent teams. And finally, 6. The missing control layer.
All right, part 1, the recursive control problem. Let's deconstruct this myth of RSI.
Think about how the theoretical RSI loop is supposed to work. A model diagnoses its own weakness, it searches for information, generates tasks, writes some code, verifies its work, updates itself, evaluates the system, and then repeats the whole shebang. Sounds totally flawless on paper, right? But here is the massive danger. Every single one of those steps is a potential failure channel. A flawed verifier is going to approve flawed data. That then trains a flawed model, which generates even worse tests. This leads directly to reward hacking and benchmark contamination. The AI looks like it's getting way smarter, but in reality, it's just gaming the system.
Now, you might be thinking, well, hey, we just need better verification. But passing a test simply isn't enough. Verification answers the question, did this pass? But it completely ignores a much deeper question. What generated this output in the first place? Passing a checkpoint is definitely not the same thing as preserving the integrity of the objective. A model might get absolutely amazing at passing coding tests, while entirely losing its ability to make sound scientific judgments.
Moving on to part 2, enter the energetic paradigm, where we look at intelligence as controlled transformation.
Okay, so what exactly is the energetic paradigm, or EP? Basically, it's a systems framework that stops treating AI like some magic text generator. Instead, it treats intelligence as a controlled energy transformation. Think of it kind of like an electrical circuit. A model isn't just a brain sitting there thinking. It's a circuit moving cognitive energy from an input through various barriers and conversions toward a stable output. Let's break that circuit down a bit. EP tracks source energy, stuff like your raw data, computation, tools, human feedback, scientific problems, even institutional goals. It then maps how that energy gets converted through reasoning, search, planning, code generation, and experimentation. But crucially, it monitors the system for barriers and losses. Like what could waste all that effort? Hallucinations, reward hacking, recursive drift, shallow optimization, sycophancy. These are all massive energy leaks. And without an overarching control layer, a self-improving system is going to amplify those leaks right alongside its intelligence.
Part 3. Solving recursive drift and preventing those embedded errors.
So what is recursive drift? It happens when small, seemingly minor errors accumulate and become structurally embedded inside the improvement loop over multiple rounds. Imagine a model acting as both the creator and the judge. A harmless, one-off mistake in round 1, probably ignored. But by round 50, because the system is verifying its own bad logic, that tiny error has amplified into a massive structural distortion. It basically turns into a blind loop feeding entirely on its own exhaust. So how do we actually fix this? EEP solves drift not with blind loops, but with strict structural separations. 5 of them, actually. Step 1. Separate problem generation from solution generation, so the AI doesn't just tee up easy tasks to inflate its own scores. Tasks have to be evaluated by novelty, difficulty, falsifiability, and strategic value. Step 2. Separate the solver from the verifier so they don't share biased incentives. We don't want the verifier just rubber stamping things. Step 3. Separate local success from global success. A higher benchmark score shouldn't cost you global robustness, and a more persuasive answer definitely shouldn't mean less truthfulness. Step 4. Track error propagation. We have to ask not just, did an error happen, but can this error reproduce itself in future iterations? And finally, Step 5. Periodic regrounding. The system has got to connect back to external reality, things like physical experiments, formal proofs, expert judgment, or cost constraints. We can't let it just hallucinate in a vacuum.
Part 4. Scientific taste and discovery. Structuring the unknown.
You know what makes a truly great human scientist? It's not just coming up with ideas, it's selecting the right ones. We call this taste. Now, instead of treating taste as some mysterious, unexplainable human charisma, EP treats it as a structural control function to rank research paths. A high-value problem attacks a real bottleneck, it creates reusable knowledge, survives rigorous verification, and unlocks future possibilities. A low-value problem, on the other hand, is just easy to measure, fashionable, and locally rewarded. An AI without taste is just going to endlessly generate low-value incremental work because it's easier to score points that way. EP actually formalizes taste to force the system to aim for real fundamental breakthroughs.
To turn this theory into rigorous practice, a discovery model has to place every single one of its hypotheses inside a strict causal system. It has to ask hard EP questions. What exact anomaly is the source? What makes this problem worth pursuing? What causal path even makes it possible? What barriers are standing in the way? What mechanism actually converts the input to the outcome? What could waste the effort? What test separates signal from pure illusion? And what governance boundary stops harmful optimization? By forcing an AI to answer these structural questions, we prevent its generation from just evolving into unchecked imagination. We ensure it's doing testable, rigorous science.
Part 5. Governing agent teams. Let's talk about structuring cognitive resources.
There is this huge misconception right now that if you just throw more agents at a problem, you magically get more intelligence. Spoiler alert, you don't. EP assigns highly specific, controlled functional roles to agent teams. We're talking decomposers, pathfinders, solvers, verifiers, adversaries, integrators, governors, and a memory layer. The core issue is absolutely not the sheer number of agents. If 50 agents just chat together in an unstructured way, you just get a diffusion of responsibility, false consensus, and really expensive noise. EP ensures that cognitive resources and information flow logically through a governed, structured circuit.
And yes, humans are still absolutely crucial here for something called expertise distillation. But future AI needs human expertise to act as a control pattern, not just a preference. We don't want a human expert just saying, "Oh, I like this answer because it sounds polite." We need the AI to fundamentally understand why the expert rejected a false path. The system has to internalize failure recognition, quality judgment, and problem selection. It must recognize hidden costs and detect fake progress. It's really about converting human judgment into reusable governance.
All right, Part 6, our final section, the missing control layer and the future of RSI. For any AI to actually improve itself without going off the rails, it fundamentally needs 3 layers. First, the capability layer. It can reason, code, and search. Second, the verification layer. It can test and critique its own outputs. But sadly, most of the industry stops right there. The energetic paradigm acts as that vital third piece, the control layer. This is the layer that preserves the system's objective integrity across endless looping cycles. Without it, the whole system, eventually, inevitably, drifts.
Look, if you take literally one thing away from this whole explainer, please let it be this. RSI is not automatically progress, it is amplification. Without a control layer, amplifying intelligence simultaneously amplifies error, bias, drift, and shallow optimization just as easily. It is a massive double-edged sword. More activity does not automatically equal structural progress.
So I want to leave you with this final provocative thought. The big challenge moving forward is not whether AI can improve itself. We absolutely know that is coming. The real challenge is whether that improvement can remain true to its purpose. Can we actually govern the recursion? I really hope this explainer has given you a powerful new lens to view the future of AI development through objectives, constraints, and system-level diagnosis. Thanks so much for diving into this with me today.